So, wait. All right. So I hope everybody's okay after that storm. I got 9 inches of water in my basement and garage. I didn't lose any power, but I did have, I have 2 sump pumps in my basement, and I had both of the sump pumps running all night, but they just couldn't keep up. You know, they pump out to the storm drain in the street, and there was just so much rain that the storm drain in the street, you know, was just completely full. So the sump pumps just don't really have anywhere to pump the water to. So my basement, you know, filled up, and it was a mess. But it's all good now. Today's like a really nice day for evaporation, right? The sun's out, it's windy and not humid, and so it's all like empty and dried out now, and everything's good. But yeah, that was kind of bad. All right, so let's see. I posted Tuesday's class. I just did that like an hour ago or something. I didn't get to that earlier, but anyway, it's up there now. So you should have a look at that if you don't remember what we did. And let's see what else. Okay, I have to give you a little heads up in advance. I'm at home today. I was planning on going in, but the college is basically closed because of the storm. So I'm teaching from home, which is fine. It doesn't make any difference. I'm teaching remote, so I can do it from wherever. That's the whole point of remote, except that my tablet is in my office at work. So I'm using a different tablet. It's an iPad. It's different software. It works great. I should be able to handle it, but I'm just giving you a little heads up that if I fumble around a little bit, it might be, well, we'll see. Anyway, it'll be okay. All right. Does anybody have any questions about anything before we get started?
There are a few questions in chat.
There are a few questions in chat. Okay. All right. Did you send out link today? I did send the links out. Is anybody here now that didn't get the link? All right.
Professor.
Yeah. What's that? Oh, Ryan. You didn't get the link, Ryan?
I got it from somebody else.
You got it from somebody else. Okay. All right. Well, send me an email at some point asking me to look into that. I'll check. I send it through. I'm sending it through Blackboard. I believe Blackboard uses the same database as CUNY First, so it should just be going to whatever address is listed for you in CUNY First. Maybe the email address that is listed in CUNY First isn't the one you think it is, or isn't the one you're checking.
Yeah,
that's just something. Yeah, that's just something to check. That's usually the problem, is it's going to an email address that's not the one you think it's supposed to go to. And you can change that, I believe. All right. Okay, anything else? Any other questions about anything before we get started? Okay, all right. Well, let's finish. I want to finish this thing we're doing with this example with the wave equation. I basically want to finish the example, and then depending on how much time we have left, I just want to make a few general remarks then about PDEs, just to kind of usher in the topic. All right, so let's see. I'm going to share. Okay, hold on a second. Okay, I'm going to stop sharing. Okay, so already, hang on. something already different happened. Oh, there we go. Yeah, okay. iPhone, iPad. Right. Okay, do something over here. Oh yeah, pull that down. Right. Okay, thanks. I think we're good. Okay. All right, can you guys see this tablet
Yes.
that I'm
Yes.
writing on? Okay, and you can hear me all right. Is that right?
Yes.
Okay, all right. Well, okay, then away we go. Not so, away we go. Okay, all right, so here's what we did so far. We have this wave equation that's describing this vibrating string. So it's stretched between these 2 points and it's oscillating back and forth as it goes, like a guitar, just think of a guitar string. And we found a solution. And the solution is the sum as n goes from 1 to infinity of b sub n times the cosine of lambda nt times the sine of n pi x over L. Lambda n is n pi c over L. C is just this constant that depends on the string. All right, so you can verify easily by just computing the partial derivatives and plugging them into the equation that this is a solution. But in fact, this is a very general solution. Essentially, any solution looks like this. Now, the question is, what are the coefficients? Well, the coefficients depend on the initial condition. So if you plug in 0 for t, then you get some function f of x, which is the initial position that the string is in before you let go. And so if you plug in t into this equation, t equals 0 into this equation, then you will get f of x, and you'll end up writing f of x as a linear combination of these sine functions. And so we call that the Fourier sine series of f. And so if we can compute the Fourier coefficients, that would be these b sub n's, if we can compute those coefficients in the case of a particular f, we'll have an explicit solution for our problem. Okay, so last time we came up with a formula for the b sub n's using that orthogonality condition that's satisfied by these sine functions. We got the following formula: b sub n is equal to 2 over L times the integral from 0 to L of f of x sine n pi x over L. So there's an explicit formula for the coefficients. So we can now apply this to an example. All right,
Professor?
so yes.
Sorry, somebody just noticed that I don't think we're recording this class.
Oh, yeah, that's because I forgot to resume the recording. I paused it before we got started. Okay, thank you for pointing that out. Okay, so now we're
recording in progress.
And now I'm going to resume the sharing. Oh, I have to go through this. Oh, I guess I have to go through this thing every time. Okay, that's all right. I can do it. Share mirroring. Okay, now we're recording. Now we should be recording, and you should be able to see the tablet again. Is that right?
Looks
Yes.
good.
Okay, good. All right, so let's do an example. Okay, so the example that I have in mind is the following. Let's take the guitar string and grab it right in the center and just pick it straight up, hold it taut like that. So this height right here is also L/2. Just pick it up in the center and pull it straight up, comes to a point, and then let go, and it'll vibrate. And let's solve that problem. Okay, so f of x is given by, well, it's two pieces here. It's x between 0 and L/2, and it's L minus x between L/2 and L. Okay, now what we need to do is to extend f to a odd 2L periodic function, right? If you go back to this business of computing the Fourier series, this was really 1 over L times the integral from minus L to L of f times the sine. But it just so happens because f is odd and the sine is odd, their product is even, so I can simplify it by going from 0 to L and doubling. But we're really integrating from minus L to L. So we have to go across an entire interval of length 2L. 0 to L is only length L, so that doesn't quite cut it. So that's why we have to extend it. So when we extend this function, I'm not going to write down the formula again. I'm just going to draw the picture. So here's L, here's 2L, here's 3L, here's minus L, minus 2L, etc. And so L/2 is right there. And so we went straight up. And then from L/2 to L, we went back down. All right, so over here, we're going to go, this is height L/2 here, and this is height minus L/2. So in the negative direction, we just go down, and then we go up like that. Okay, so we get this function defined on the entire real line, actually. Not just minus L to L, it's defined on the entire real line. We call this a triangle wave. All right, and so that's our function, and we just need, yes.
So I understand, like visually, this is sort of intuitive to make it a wave, but when you're creating the odd periodic extension, you just make it the negative of whatever it is on the right side.
Yeah, the function, okay. Yeah, an odd function satisfies.
Right.
This is the definition of an odd function, right? So what you do is you take the values of f from 0 to L, and then you just use this formula right here to get the values from 0 to minus L.
Okay, sounds good.
So that's all. Yeah, that's all you do. Now you have it. Now you have it from minus L to L, which is an interval of length 2L. Then you just repeat it. So every block of length 2L, you just repeat that pattern.
Right. Thank you.
And then that's it. So that's how you get the odd 2L periodic extension of the function. And the reason we do that is because we have to sort of have this function on an entire interval of length 2L in order to use our orthogonality condition. Remember, the orthogonality condition for the sine function was a formula involving integrating from minus L to L. So we needed a whole interval of length 2L in order to get that and do this whole calculation. Now, at the end of the day, we're only really interested in f of x from 0 to L, because that's the only portion that applies to our original problem, right? The guitar string goes from 0 to L. So in the end, that's all we care about. But we have to kind of do this intermediate thing to do this. Okay, so all right, is that okay? Does anybody have any questions there? Or all right, so now okay, well now let's proceed. So so we're going to compute b sub n, which is 2 over L of the integral from 0 to L of our function. And because the function is given by two formulas on the two halves, we have to actually break this up into two integrals. So we're going to have 2 over L from 0 to L over 2. And on the interval from 0 to L over 2, f of x is just x. Okay, and then on the other piece, it's 2 over L times the integral from L over 2 to L of L minus x of sine n pi x over L dx. Now, let's see, this is 2 over L, 0 to L over 2. I'm just repeating this first term, n pi x over L dx. Now for this one here, I'm going to split this up because I have L minus x. I'm going to multiply that out and split that up into two pieces. And in the first term, the L's are going to cancel. So I'll just have 2 times the integral from L over 2 to L of sine of n pi x over L dx. And then the second term will be minus 2 over L times the integral of x sine n pi x over L dx, also going from L over 2 to L. So I've split the thing up into 3 terms, 3 integrals, and we have to do each of those 3 and add up the results, and that'll be the answer. Okay, so let's do this computation. I want you to be able to do this kind of computation by hand. This is a very typical problem. So by doing this problem, you're getting introduced to just sort of the typical computational techniques you use to do one of these. You know, if it's a triangle wave or a sawtooth wave, or, you know, they're all kind of similar. In particular, we're going to use integration by parts. So I want to make sure you remember how that goes. Okay, so let me just label these things. I'll call this one 1, and this one 2, and this one 3. And let's just do them one at a time. And, you know, it's helpful to keep organized and keep everything straight so that you don't get confused. It's easy to make a computational mistake. It's easy to make a sign error. So it helps to kind of be organized. So that's why I'm kind of organizing it out like this. All right, so let's do 1. Okay. Well, actually, no. Let's not do 1. Let's look at this thing and notice that in 1 and 3 we have the same integrand. It's x times sine of n pi x over L, which we're going to do by integration by parts. So it's going to be the same integration by parts for both 1 and 3. The only difference between 1 and 3 is the first one is evaluated from 0 to L over 2, and the third one here, it's evaluated from L over 2 to L, and one has a 2L in front and one has a minus 2L in front. So the particulars after we integrate are going to be different when we plug in the numbers, but the basic integral is going to be the same for 1 and 3. So we only have to do this integration by parts once. Okay, so let's just do that. So this is kind of a subroutine here. Let's see, hang on a second. I want that, that, okay. All right, so it's, why is that not? Oh, okay. So the integral of x sine n pi x over L dx, I'm going to call x, I'm going to call that part u, and I'm going to call this part dv. Okay, so if this is u, if x is u, then du is dx, and v, well, if I integrate the sine, I get minus the cosine. And then I have to put this constant in front, inverted, so that it cancels out. So that's v. So integration by parts. Well, let me remind you of the integration by parts formula. The integration by parts formula says the integral of u dv is equal to u times v minus the integral of v du. Okay, so hopefully you know that formula. All right, so what we get is we get u times v, so this is going to be minus L over n pi x cosine n pi x over L minus the integral of v du. Okay, so v is this thing with a minus L over n pi in front, so I get minus a minus. So the minus signs cancel and it's plus. And du, it's v du. Du is just dx. So that's just dx. So what we get is we get minus L over n pi times x cosine n pi x over L plus, well, I have to do this integral. So I have L over n pi times this integral. So the integral of the cosine is just the sine, because the derivative of the sine is the cosine. So it's sine n pi x over L, and then I have to bring out an L over n pi to cancel out. And so the L over n pi gets squared. All right, so using integration by parts, the integral of x times sine n pi x over L dx is equal to minus L over n pi x times the cosine of n pi x over L plus L squared over n squared pi squared sine n pi x over L. Okay, so we're going to use that. All right, so moving on, that means that 1 is given by, so 1 is 2 over L times the integral from 0 to L over 2 of x sine n pi x over L. And so that's 2 over L times, and then we just got through showing that it's equal to this thing, which I can copy like this. Well, sort of. Yeah, all right. And then I'm evaluating this from 0 to L over 2. Okay, so now you just plug in when you plug in, first of all, notice when I plug in 0, the first term is 0 because I have an x there. And when I plug in 0, the second term is also 0 because I'm going to get the sign of 0, which is 0. So I'm only going to get the stuff that I get when x is L over 2. And so it comes out to L over n pi times the cosine of n pi over 2 plus 2L over n squared pi squared sine of n pi over 2. Okay, that's a little messy. Let me sort of clean that up. N squared pi squared. Okay, so that's the answer to 1. It has 2 terms. All right, now if you do a similar thing for 3, the third integral, I'm doing 1 and 3 because 1 and 3 both involve that integration by parts calculation that we just did. So if you do the same thing for the third integral, you're going to get the following. I'll write out the answer. You get 2L over n pi. So you should check this yourself. Just plug in the limits and multiply by minus 2 over L. And you should get the same thing. L over n pi cosine n pi over 2 plus 2L over n squared pi squared times the sine of n pi over 2. Okay, now you might object here and say, well, how come there's only 3 terms here? Shouldn't I have gotten 4 terms? Because I'm taking this expression for this thing, and I have 2 terms. And when I evaluate from L over 2 to L, I should get a total of 4 terms. But what happens is when you plug in L into the second term right here, notice that you get sine of n pi, and sine of n pi is always 0. No matter what n is, sine of an integer times pi is 0. So one of the 4 terms is actually 0. So that's why you only end up with 3 terms. Okay, so we have these 2 terms for integral 1. We have these 3 terms for integral 3, and now let's do integral 2. Integral 2 is actually the easy one because it doesn't involve an integration by parts. Okay, integral 2 was just 2 times the integral from L over 2 to L of sine n pi x over L. That's all that was. And so that's 2 times the integral of the sine is minus the cosine. So I have minus L over n pi times the cosine of n pi x over L, and this is being evaluated from L over 2 to L. So that just comes out. So that one's easy, and that just comes out to minus L over n pi times the cosine of n pi over 2 plus the other term, which is 2L over n squared pi squared times the sine of n pi over 2. Okay, so we just get those 2 terms for integral. I think I wrote down the wrong thing. Yep, sorry. When you evaluate the second integral, you get minus 2L. It's staring at us right in the face up here. It's minus 2L n pi cosine n pi plus, because the minus signs cancel, 2L over n pi cosine n pi over 2. Okay. All right, so we did it. So basically we just use this formula. So let's just recap what we did. We took the formula for the Fourier coefficient, the odd series Fourier coefficient, and we plugged in our function f of x, which has two different formulas depending on which half of the interval you're on. So you have to actually break it up into two intervals. And then I split the third interval up into two terms, and I got these three terms. And we use integration by parts on the first one and the third one. And the second one, we didn't have to use integration by parts. That's much easier. And we ended up getting all these terms. And so now we just add them all up. And what you'll notice when you add them all up is that here I have a minus L n pi I have a minus L n pi cosine n pi over 2. And then over here I have another minus L n pi cosine n pi over 2. So that's minus 2 L n pi cosine n pi over 2. And then here I have a plus 2L over n pi cosine n pi over 2. So all the cosine n pi over 2 terms cancel actually. Okay, now let's see. Let's look at the sine. Let's look at the cosine n pi terms. I have a 2L n pi cosine n pi here. And I have a minus 2L over n pi cosine n pi there. So those just cancel out. And so it looks like all we have left is just this term plus this term. So that's 4L over n squared pi squared sine n pi over 2. So that's it. So we have B sub n, our Fourier coefficient B sub n is equal to 4L over n squared pi squared sine n pi over 2. So we're essentially done. Let's just clean things up a bit by writing out the solution kind of neatly. So first of all, let me just point out something. The sine of n pi over 2, if n is even, then n over 2 is an integer. And we have the sine of an integer times pi, that's 0. So this is always 0 when n is even. Now, if n is odd, then this is not 0. Like the sine of pi over 2 is 1, the sine of 3 pi over 2 is minus 1, the sine of 5 pi over 2 is 1, etc. So when n is odd, it's non-zero. In fact, it's plus or minus 1. Now, whenever you have something that alternates between plus or minus 1 with the parity, you know, half the time it's plus 1, half the time it's minus 1, it's convenient to write that as a sort of a simple formula. There's a lot of ways to do it, but the most common way to do it, the way you see most often is you just take minus 1 raised to a power. Okay, hang on a second. I have to do not disturb here. Okay, there. I'm being disturbed. Okay. You can still see the tablet, right?
Yes.
Okay. All right. So the sine of n pi over 2, when n is odd, alternates between +1 and -1. -1 raised to an even power is +1. -1 raised to an odd power is -1. So we just want to figure out a nice little formula for the exponent. And there's a couple of ways to do it. But I'll just write it as n-1 quantity over 2. That's, that works out. And what I like to do is usually the way I do this is I guess what I think it is, and then I just check it to make sure it's right. But anyway, so let's just check this. So when n is 1, the sine of pi over 2 is +1. If I looked at this exponent, 1 minus 1 is 0, minus 1 to the 0 is +1, so that's right. If n is 3, the sine of 3 pi over 2, on the unit circle, that would put you down here. That's 3 pi over 2. And there, the sine is -1. Well, if I put in 3, 3 minus 1 is 2, 2 over 2 is 1, minus 1 to the 1 is -1. So this seems to be right. Now, sometimes you get these things where it has 4 cases, where n is either 0, 1, 2, or 3 modulo 4. In other words, n divided by 4 has a remainder of either 0, 1, 2, or 3. And then you would have 4 cases, not 2 cases. But here we just have 2 cases. N odd, well, we have 2 cases in 2 different ways. We have the 2 cases where n is odd, it's non-zero, n is even, it's 0. And then amongst the n equals odds, we have 2 cases. Half the time it's +1, half the time it's -1. So I guess this actually is a situation where there's 4 cases to consider. Anyway, so that's the answer. And so now we can go ahead and write that f of x is equal to the sum. Here, I'm just going to write it this way. Again, there's a lot of ways to see it. I'll write 1, 3, 5, ... That's pretty clear what that means. And then we have 4L over n squared pi squared sine. Whoops, I forgot the sign. That's important. -1 to the n minus 2 over 2, n minus 1 over 2 of sine n pi x over L. Also, you could pull out the constants that don't depend on n. So I could write 4L over pi squared times the sum as n goes to 1, 3, 5, etc., -1 to the n minus 1 over 2 sine. Can I excuse me for just a moment? Okay, never mind. All right. Okay, does anybody have any questions about this?
What was the n in the last expression?
Oh, I'm sorry.
N
I'm sorry. Typo. You're talking about the 1 over n squared that I left out. Yeah. Sorry about that. Okay. Yeah, there we go. So what we've done is we've written this function here, this triangle function from 0 to L. We've written it as a infinite sum of functions. Now, I suppose, you could say, well, this is like a really complicated expression, and this is actually a pretty simple function. So why did we take a simple looking function and write it in such a complicated way? But, this expression, this is a kind of an amazing expression. I mean, it's first of all, notice that all the terms are differentiable. So the function that we started with is not differentiable. It's got a peak, in the middle, but we're somehow writing it as an infinite sum of differentiable functions. So that's interesting right there. Just the fact that we can take this non-differentiable function and sort of approximate it as close as we can by a differentiable function. So that's an interesting fact. But the really interesting fact is that each of these terms is harmonic. Well, it has an amplitude. It has an amplitude that depends on n. But but remember what the picture looks like. We have this, and then we have this one, and then we have this one. So what we're doing is we're breaking up this waveform into its constituent harmonic pieces, and that has all kinds of implications for all kinds of things. All right. Now the other thing though is, oh yeah, go ahead.
Yeah, this might be off topic, and if not, we can cover it after class or whatever. But then, like, isn't there the theorem that says if you add a bunch of continuous functions together, you're gonna get a continuous function?
Well, yes and no. So there is a theorem that says that if you have a sequence of continuous functions and you form their infinite sum, then if it converges uniformly, then the infinite sum is continuous. But you have to assume that the convergence is uniform. If the convergence is not uniform, then the infinite sum might not be continuous. So that's the catch. Yeah. And in this case, so that raises a question about Fourier. So we're going to talk about convergence of Fourier series. We're going to get into that and state and prove some theorems, but just not yet. But yeah, so when we do that, we're going to define uniform convergence and deal with that a little bit, because uniform convergence is also important. Let's say you wanted to take the derivative of f. You might say, well, the derivative of f is just going to be the sum of the derivatives of each of the terms, because that's how you differentiate a sum. But when it's an infinite sum, you have to be careful. It's not always true. You need some hypothesis like uniform convergence, or maybe even something a little stronger. So all those issues we're going to get into a little bit as we go along. But yeah, that's a good question. You're asking about you're getting into the whole question of whether any of this makes any sense or not. I'm doing what Fourier did in the 1800s, when the concept of convergence wasn't even defined yet. The concept of continuity wasn't even defined yet. They didn't have epsilon and delta definitions of continuity. So Fourier just wrote all this down and expected everybody to buy it. And some people bought it and some people balked at it. Euler balked at it, and Euler was the greatest mathematician of that time. So, but anyway, but it turns out under appropriate hypotheses, it all works. So it's, there is a whole working theory here. Okay, so I'm just doing the whole hand wavy thing that Fourier did, a couple hundred years ago. All right, here, let's write down the solution to the original problem, because that's the whole point of all this. So let's not leave that out. That's the payoff to all this work for all these hours. This is the payoff to the whole thing. So if I can get my stylus going here. Okay, so we're going to get 4L over pi squared of the sum over the odd integers. So this only has odd terms, -1 to the n-1 quantity over 2 cosine. Okay, here, hang on a second. I really do have to do something here. I'll be Okay, I'm back. Sorry about that. Okay, so we have the cosine of lambda nt. Remember, lambda n was n pi c over L times the sine of n pi x over L. So that's it. So we've written down the solution to the particular example that we did, where you grab the guitar string in the middle, pull it up tight into a triangle, and then let go. Now, if you started out with some different initial position, then you would get some different formula for the solution. Also, if you started with an initial velocity, then you would get a second term that involved a Fourier cosine series. So this is really only half of the picture, because we're assuming that the initial velocity was 0. In general, the initial position will give you a Fourier sine series, and the initial velocity will give you the terms of the cosine part, the Fourier cosine part, for the wave equation. Okay, so does anybody have any questions about that?
I think the 1 over n squared term might be missing from this one too.
I'm sorry. Sorry, I keep forgetting to write it down. I wrote it down. I wrote it down before. I forgot to write it down on the previous page, and I forgot to write it down again. I pulled out the 4L over pi squared out of the sum because they don't depend on n, so I can bring those out front, and the 1 over n squared has to stay inside, because obviously that depends on n. So okay. So, all right, well, so there we go. That's how you can solve a boundary value problem involving the wave equation. Okay, let's see, let me clean this up a little bit. All right. So now, in the remaining time, I want to kind of switch gears a little bit and just talk about sort of some general aspects of PDEs. Okay. So in particular, I want to sort of point out how the theory of PDEs is really quite different from the theory of ODEs. So that's something to kind of keep in mind. Okay, so in general, with here, let me write. I'll title this PDEs versus ODEs. Okay, so with ODEs, an nth order equation, generally speaking, an nth order equation will have a family, a collection or a family of solutions, call it a collection or a family of solutions which are indexed by n constants. Okay, so for example, if I have you're familiar with the theory of linear equations. If I have a linear nth order ODE, I'm thinking of a function of one variable, a function of one variable, linear, let's say it satisfies a linear nth order ODE, let's say with, let's say it has constant coefficients, then what you'll get is you'll get a solution which depends on some initial which depends on some set of constants, some set of n constants. And if you have initial conditions, you can solve for those constants. So like, let's say it's a linear second order ODE describing, a vibrating mass on a spring or something, then you'll get a solution that'll depend on two constants, C1 and C2. And then if you put in the initial position, that will determine the first constant C1. And if you put in the initial velocity, then that'll determine the second constant C2. And then you'll have a precise particular solution to your particular initial value problem. And then same thing if it's third order, you'll get a depending on three constants. And then if you had three initial conditions, that would determine those constants, and that would be it. Okay, so that's not exactly what happens with PDE. Well, something sort of analogous to that happens, but it's more complicated. So let's just illustrate with a simple example. Let's say we had the following PDE. So this is just going to be a simple first order PDE. The partial of u with respect to x is y times the sine x. Okay, so our function u, this is a PDE. So u is a function of two variables, x and y. All right, so what's the natural thing to do? Let's integrate with respect to x, and that will give us u. So if I integrate this with respect to x, I'll get minus y cosine x, but I have a constant of integration, but that constant of integration is only a constant as far as x is concerned. It's not necessarily a constant as far as y is concerned. So the constant of integration is actually a function of y. So you see, what we did was we solved this sort of general first order PDE, and we did get a solution that depends on one entity, just like when you solve, going back to what I said here, when you solve a first order ODE, you get a solution that depends on an entity. But in the ODE case, that entity is a number. But in the PDE case, that entity is actually a function. All right. Now let's do another example just to illustrate the same thing. Let's say we had a second order PDE. Let's pick the simplest one we could sort of think of. So here's a second order again, u is a function of x and y. All right. So what are we going to do? So we'll integrate with respect to x. And so this will give us this is just going to be the integral of 1 with respect to x. So we're going to get x, but we have a constant of integration, which I say constant, meaning constant as far as x is concerned. All right, so we get that. And then we want to go one step further to get u, to solve the equation. Okay, so we integrate this, and we're going to have to integrate x plus f of y, so we get x squared over 2 plus x times f of y plus another constant of integration, which I'll call g of y. Okay, so you see your second order PDE has a solution. It's right there. But instead of depending on two constants to determine the particular solution, it depends on two functions. All right, and this was a very simple equation. And yet the general solution is a rather complicated thing because it depends on two functions, not two constants. Okay, so that's kind of one of the differences between PDE, one of the main differences between PDEs and ODEs, which makes the situation with PDEs a lot more complicated. So what you'd be tempted to say then is that in general, if you have an nth order PDE, let's say in m variables, we were looking at two variables, but let's say you have m variables. If you have an nth order PDE in m variables, the solution should be a family of functions, a collection of functions. So you can have a whole bunch of solutions, a family of functions, and they should be indexed by, well, it's an nth order equation. So we're going to have a general solution that's indexed by n functions of, now let's see what happened here when our PDE involved the function of two variables. Our so-called constants of integration were functions of one variable. So to generalize that, if we had m variables, these should be functions of m minus one variables. So this is sort of the idea. This would be analogous to the fundamental existence theorem for ODEs. This would be sort of your guess for what the fundamental existence theorem for nth order PDEs should look like. Except it turns out this is actually rather difficult to pin this notion down and make it precise and actually prove it. So difficult. So this is the idea, and it's kind of true in spirit. I mean, it's definitely a good way, kind of the right way to think about it. But to turn this into a precise theorem and then actually prove it, which we're not going to do, by the way, just in case you're worried, we're not going to do this. It's too hard. It would take too long. You might do this in a graduate PDE class or something. You would do this. This is difficult to make precise and prove. But it's the right idea. Okay, so all right. Does anybody have any questions about that? Okay, this is just something to kind of get you started, get the wheels turning, and get you started thinking about the difference between PDEs and ODEs. Okay, all right. Well then, all right, so then the next thing I want to do, now let me just check in here for a moment. See how you're doing. Okay, doing okay, all right. Okay, so far so good. All right, so now let's I'm going to say one more thing, and Oh, wait, I missed. Yeah, I'm sorry. I remember I'm operating in a different. I actually kind of like this tablet, this iPad with this pencil. It's pretty good. I don't know. Maybe I'll. Well, anyway. Wait, hold on a second. Wait, I have a problem. Unable to share, unable to connect. Okay, so hold on. Now suddenly it's not working. Wait, just give me a second. I thought I did the exact same thing I did before. Maybe the Wi-Fi network switched. Let's see, what am I on? I'm on that one. Okay, let's see. All right, let me try this one more time. Share iPhone, iPad via AirPlay. Choose Zoom, Robert, MacBook Air, screen mirroring. Oh, okay. All right, I have no idea what happened there. Okay, all right, everyone, you can see the screen?
Yes.
Okay, all right. So, okay, so the last thing I want to say is just kind of a little bit of terminology. Okay, so first of all, because PDs are so complicated, and because it is really such an involved subject, we are primarily going to focus in this class on linear equations. So I don't know, I maybe didn't say that before, but we are really going to focus almost entirely on linear equations and not get into nonlinear PDs at all. Also, we're going to, for the most part, focus on linear second order. That's going to be, that will include all these famous examples like the heat equation and the wave equation and Laplace's equation and Schrodinger's equation and whatnot. That's plenty to keep us busy for one semester. So we're going to focus on linear second order PDEs. And so if you had such a thing, what would the sort of general linear second order PDE look like? Let's say u is a function of x and y. Okay, then I could start writing down the various partial. Here's the second order partials, and then I would have the first order partials, and then I would have a 0th order partial. And let's say that the coefficients are constant, just for the sake of argument. So A, B, C, D, E, and F are constants, just suppose. Okay, so this is a linear second order PDE with constant coefficients. Now, it turns out you can actually write a linear second order PDE that's a little bit more complicated than this, but you can always show, there's a theorem basically that says that, well, no, actually, no, never mind. That's not what I mean to say. Yeah, this is the general linear second order PDE. Okay, so what we do is we sort of classify these things. If you look at this discriminant, this b squared minus 4ac discriminant, this involves the coefficients of the second order partials. If this is positive, then we call the equation hyperbolic. And if it's equal to 0, then we call the equation parabolic. And if it's equal if b squared minus 4ac is negative, we call the equation elliptic. Okay, so all second order linear PDEs with constant coefficients can be classified as either being hyperbolic, parabolic, or elliptic. So this is just very common, famous terminology that you hear all the time. And so let's see how this applies to the sort of famous examples. So let's see, the wave equation, the one we just got through doing an example of.
Wait, sorry, can you go back for just a split second?
Sure.
Thanks.
Okay. All right. So the wave equation, which looks like the second partial with respect to t minus c squared u, the second partial with respect to x equals 0. Oh, well, actually, I'm sorry. This is a sort of bad notation here. This c is not the same as this c. Here, let me call this, I'll call it c tilde. Sorry about this. This c is the coefficient. This is the coefficient of the second partial with respect to the second variable, which has nothing to do necessarily with this c here. This c here is the c that I was using before. You know, usually when we write the wave equation, there's this constant that depends on the elasticity and the tension on the string and whatnot. And that's what I mean here. Okay, but anyway, so here's the wave equation as we were writing it before. And so then you can check that this is a hyperbolic equation. So the wave equation is hyperbolic. And then if you look at Laplace's equation, which is one of the most fundamental partial differential equations of them all, Laplace's equation, if you look at Maxwell's equations, which describe the electric and magnetic field, the dynamics of the electric and magnetic field. So basically all of electromagnetism is encapsulated in Maxwell's equation. And if you combine those four equations into a single equation, it's just an example of Laplace's equation. So this is actually all of electromagnetic theory right here. And so that's an elliptic equation. And then thirdly, let's say you're on Wall Street and you want to write down functions which describe the value of very complicated derivative securities like various instruments based on stock options and stock futures and commodities futures and things like that. Then you're going to write down some version of the heat equation, which looks like this. Or if you're Fourier and you just want to understand heat literally, just the diffusion of heat through a metal object, then you're going to write down the heat equation, which notice it's very similar to the wave equation, but it only has first order partial with respect to t rather than the second order partial with respect to t. So, but that makes a huge difference because that means that the heat equation is parabolic. Okay, so that's just some a little classification, which gives you some terminology that gets used quite a bit. So now you know what those terms mean in this context. And
Professor,
yeah.
Why is the last one parabolic?
Why is the last one parabolic? Well, let's see. because, oh, again, this C has nothing to do with the other C, but so let's say, okay, so let's say X was X and Y was T, okay, then we have the coefficient of UXX is minus C. All right, so A is minus C, this C. Sorry about the proliferation of C's here. So the A in this equation right here is a negative number. And B and C tilde are both 0, right? There is no mixed partial or second partial with respect to T. So B squared minus 4AC is 0, because B is 0 and C tilde is 0. Yeah, forget about A, it doesn't matter. B is 0 and
Thank
C tilde is 0. So it's 0, so it's parabolic. That's all.
Thanks.
Okay, yeah. So that's parabolic. Okay. So, all right, anyway, well, that's it. That's all I got for today. This, by the way, there's a little bit on the homework on this. There's a homework, there's a couple of homework problems that deal with solving a first order PDE. Oh yeah, I should just mention that. So you can actually just solve first order PDEs. First order PDEs are not that hard to solve, even nonlinear ones. You can actually just solve them. It's not that hard to do, really. I mean, second order and higher, it's just way more complicated. But first order PDEs, you can actually just make a few substitutions and hack around and kind of solve it. Or, well, I should say first order linear. Maybe nonlinear is a different story. But first order linear is just kind of directly solvable. And so there's a procedure that is given in the book with some examples, and you have some homework problems on the first homework assignment, which you can do, which are examples of that. So I don't necessarily, maybe what I'll do is just work out an example and record it and post it so that you can look at that. Or you can just look at the example in the book and kind of emulate that method, and you should be able to get that. So, okay, all right. Anybody have any questions about anything?
So we're not meeting on Tuesday?
Oh yeah, correct. Yeah, Tuesday. Yeah, that's correct. We are entering a kind of an extended holiday weekend. So there's no classes Friday through Tuesday. So that's 5 days in a row with no classes. So you won't be going to class again until Wednesday. So you have a five-day weekend, and then we meet again next Thursday.
Yeah, school's actually closed Wednesday as well.
Wednesday is, yeah.
Yeah, Rosh Hashanah is Tuesday and Wednesday.
I'm sorry, I messed that up. It's the third. Yeah, I'm sorry. You're correct. It's the 3rd through the 8th. Yes. Sorry. You have it's a 6-day. Yeah, it's a 6-day break. You are correct. So you don't have any classes again until a week from today, and that's when we meet again. Okay, but I might give you some more homework problems during that time. Because you might just whip right through assignment 1 and then you want to keep on going, keep up the momentum.
That's right? What you're worried about? You're worried about us going too fast through the homework?
Yes. Yep. That's what I'm worried about. Okay. All right. Anything else?
Is there a specific section for us to read?
Yeah. Good question. Okay, yeah, that's a good question. All right, so let me just, so basically what we're, okay, so here's essentially what we're doing. We're just kind of talking about chapter one. You know, chapter one has this, just kind of this preliminary discussion. They talk about the wave equation as an example, and they kind of use that to introduce Fourier series. And so just, you know, read chapter one and work on the homework problems. But then we kind of got into Fourier series a little bit more. We did the orthogonality, which is 2.1, and we worked out the formulas for the Fourier sine series. So that's really you know, 2.1, 2.2, 2.3, and 2.4. So your goal, yeah, so your goal should be able to, as far as the book is concerned, you should read chapter one and then plunge into chapter two and try to get up through, get through like section 2.4. When we resume, we're going to do the Fourier expansion of a function in a little more generality. We're not going to assume it's an odd function necessarily. It'll be an arbitrary function, not necessarily odd or even. And so the Fourier series will have sine coefficients and cosine coefficients mixed together. And so we'll just kind of do that general thing, and we'll state a theorem about convergence. So remember, there's still, there's this whole big question. When can you write down the Fourier series of a function? If you write down the Fourier series of a function, when is it equal to the function? Can you differentiate it or integrate it term by term? These are all the sorts of mathematical issues that you get into when you start doing this sort of thing. So we'll start tackling that. We'll state a very basic fundamental Fourier convergence theorem, and then we'll kind of sketch the proof of it. So that'll be interesting. We're going to kind of go back and forth between theoretical mathematics and applications to applied problems. I'm hoping to kind of, do both. Okay, all right. Anything else?
So I have a question about a specific homework problem. I can stay after, it doesn't have to be.
Oh yeah, okay, yeah. Well, why don't we, yeah, okay, so let's start that now. And we'll sort of segue from class into office hour. So if you want to go, you can feel free to go. If you want to stay, feel free to stay.